This is the last case of nonlinear programming, linear objective and nonlinear constraints. And we talked about the thermlock corporation, and it has two ingredients, rubber and oil. And we have this minimizing the cost and also the constraints, three constraints over here. And notice that they are um, hardness and tensile and elasticity, and they are continuous variables. And it includes nonlinear components in the constraints only, but not in objective function. So I set up as x1 and x2, and then all the variables that we have to use over here in objective function. And then I added the coefficients of 5 and 7 for corresponding coefficient there. And then here is we have this sum product function of first row and second row that gives you cost, and you have to minimize that. And then we are now on constraints. I added these three constraints here, and then use the function to do this, right? And right-hand side, I added there. And these are the changing cells. And once these variables are determined, then this is going to be determined. And that will give you left-hand side value and objective function value. So let's go to data and solver. And let us now use that. So here's some our objective function, and this is changing, right? And you have to add Q3 and S14, Q15 and S15, Q16 and S16. And as they are continuous variables, I did not add integer or binary constraint here, and make sure that it's non-negative and GRG nonlinear programming, because we have nonlinear functions here. And then solve. Okay, it's solved, and it gives me answer and sensitivity analysis. So I'm going to produce them. So it says that it's going to be 3.32 for x1 and 14.67 for x2. So rubber has to be about 3.32, and oil has to be 14.67, and that is going to minimize the cost. And that's what we find. And accordingly, we find the calculated corresponding values for x1, x1 squared, x1 tripled, x2, and x2 squared values right here. And the cost is about $119.33. And the left-hand side and right-hand side is determined here as well. So that's what we can see. And I just want you to go to answer report. If you go to answer report, you see that first one, hardness is not binding, and you have about 11.01 of slack. So if you want to cut something off, hardness might be something that you can consider to cut off a little bit. And the second, tensile strength and elasticity, is binding. They are binding variables, so they are very important, and lifting this binding constraint up is quite serious for this cost minimization. Let us also look at sensitivity report, and as I explained before, we see this Lagrange multiplier, and the Lagrange multiplier tells us that how much you can really how much it will increase the cost. For example, 1 unit of tensile strength on the right hand side resource will increase 0.002 1 of cost. That's what it means. Similarly, you can do the same thing for the elasticity. 1 unit of elasticity on the right hand side will increase how much? $7 of the total cost, right? So you see that increasing elasticity would be a very serious one. In other words, decreasing elasticity by 1 will be decreasing about $7 of the cost, which is quite high. And the same goes with tensile strength. They are both binding constraints. So that's how you can read and interpret and understand the impact of these constraints in your optimization. Thank you.